They took paper out of there a couple of semesters ago. All right, so I have something for you, I think. I know I have something. I mean, most of us are math people, so, you know, we could probably figure out what we need on the final to pass the class and all that stuff, but I just did it for you. I still don't know what that quiz grade is, or that exam quiz, we call them quizzes, what that quiz grade is that you just handed in. So what I'm going to give you, it's going to have your name, give you a strip of paper. It's going to have your name. It's going to have 4 numbers on it. I have dropped your lowest take-home quiz already. I've put in all the bonus that I have. Your grade should be completely up to date. You can put it right there. It should be completely up to date. All right. There's nothing left, as far as I know, to put in there. I'm going to pass back your stuff. You can just go through this pile and grab your stuff out of here. So when I give you this strip of paper, the first number you see is what you would need on the final to get an A in the class. Now, the final and this together have to average out to be that number. Well, it's not even average because the final's worth more than that. So it gives you a close enough idea of what you need for an A. The next number is what you need for a B. The next number is what you need for a C. And then the last number is actually where you stand in the class right now. All right? Jose Aguilar? It's Aguilar. And then Jose Rojas. And let me see. Alexandra? Allie? Right? You like Allie, right? Okay. Diego and Tamara. And Josh, Patrick. What's that? There might be more. That's a bunch of old stuff I have. See missing anyone here? Raul, it's not here yet. Any questions on what I just gave you? All right, let's try and pick up where we left off. Oh, on Canvas, I posted the last 2 finals I've given in this class. Okay? And one of them was one I did in summer, and it focused mainly on the material towards the end, like Chapter 13 material, because in the summer we had another test right before it. So that final is not quite as long and doesn't cover as much material. The other one that's from, it'll say 2415 exam, final exam, that's what it'll say. That one is more robust. I'll bring it up so you can see it. You know how to get to the Canvas, right? Do I need to bring it up? It has the key. I mean, like, I think it has the problems worked out, but I haven't checked the key. So if you find an error in there or something like that, just let me know. Raul, got something here for you. This is, without what you're going to turn in today, this is what you would need on the final for an A, for a B, and to pass the class. This is your average right now in the class. Okay? All right. So how far did we get? Did we do that one? Bless you. Again. Okay, so we did do this one, right? Did we get to S2 on this one? No, I showed you 3 different ways, didn't I? Okay, so we still have to finish this problem up. Remember this one? We were trying to find the flux over this entire surface. We had looked at the surface S1, which was a disk. It was this problem here. And I showed you in class last time that there were 3 different ways to evaluate the flux through S1. The first way was a bit tedious. We got pi. The second way was treating S1 as a special case. We still got pi. And then the last way was to use the normal vector approach. So we had those 3 equivalent forms. So those were the integrand parts of the different formulas for flux. So let's go back now and look at S2. So we have to define what S2 is here. So help me out here. How are we going to define S2? How would you like to approach this? I give you the equation y equals x squared plus z squared. So how would you like to define this S2? Which approach do you think is going to be the most useful to us? The one where we look at the normal vector, the one where we look at the cross product of the partials, or perhaps a special case? Cross product would work, or special case if we can look at one of the variables as being dependent on 2 of the others. So is one of the variables dependent on 2 of the others? Yes, y is dependent on x and z, right? So the special cases we had, these were the special cases. When x was a function of y and z, we had that the flux turned into this. When y was a function of x and z, that's what we've got, right? Y is a function of x and z. Then we can use this double integral right here. So that's what I'm going to go for here, okay? I'm going to go for this one right here. Do y'all have any questions on why or what I'm doing? Okay, here we go. So for S2, which was y equals x squared plus z squared, I'm going to now look at y as being a function g of xz. I also need to define my vector field f as PQR. What was the vector field for this problem? It was so long ago, we've probably forgotten what the vector field was. Here it is, 0, y, negative z, right? That's our vector field. So that's our PQR. Zero, negative y, z. Y negative z. So according to this, y is a function of x and z, I need to do the flux integral. It's going to turn to the double integral over d, where d is the domain of what variables for us? D is our restriction on xz, right? xz. Yes or no? I mean, this is the first one is the flux over the surface, right? If you use this formula, you're going to convert the surface, right, into a domain of the variables which draw your surface, which for us are the x and the z variables that draw it. Because y is a function of x and z become our domain variables. So we have flux, okay, so this over S2, let's put S2 there, of f dot ds is equal to, because it's a special case, the double integral over d of, we're going to do negative p partial g with respect to x. Negative p for us is 0 times partial g with respect to x, which would have been what? 2x, it's not going to matter. And then, what? Plus q, which for us will be plus y, right? And then what? Minus r. So for us, minus r would be what? Plus z times the partial of g with respect to z. What's the partial of g with respect to z? 2z? All of this dA. We good? All right, so this becomes double integral over d, cleaning up here, y plus 2z squared dA. Do you see any issues here? My double integral, my domain is supposed to involve what two variables? X and z, right? X and z. But my integrand has y in it. But I can substitute, right? What is y? It is x squared plus z squared. So I'm going to replace this y with x squared plus z squared. So this double integral now becomes what? Double integral over d, x squared plus z squared. So x squared plus 3z squared dA. Now I need your help to get my restrictions on the domain. So what are your restrictions on the domain? Here's your picture, right? If you want, let me flip it up like this. Do you agree if I flip it like this? The ground is your xz plane, right? Y-axis is this way. So I'm asking, what is the domain that draws that bowl, right? Not the cap, not the top of it, but just the bowl itself. What's the domain that draws that? Circle, right? On the ground, it's actually that circle down right there, which has a radius of what? 1. Why does it have a radius 1? Because the top edge of this paraboloid, right, the y-coordinate stops at 1, which means if this is 1, that means this y is 1, which means x squared plus z squared is 1, which means it's a circle radius 1. So I know that on the ground, I need to plug in all the points on the ground that are going to get mapped up, we'll say up, into the surface. That domain on the ground is a circle, right? So what am I going to need to do? What's that? Parametric? Yes, kind of. Convert to polar. I mean, I have to go to a polar integral here. Now, I know last class we talked about, converting to polar. I'm looking at you because I think you brought it up, right? A little bit? No, maybe? The reason why we have to go to polar here is because we did not use this version here. We're using the special case, which means we're back to a double integral. When we first learned double integrals, we're just trying to figure out what a double integral is over a region. Our region happens to be a polar region. So we're going to convert everything to polar. So if I'm going to go polar here, can you tell me what my conversion is going to be? Yes, we're in the xz plane as our domain. X equals r cosine theta, z equals r sine theta, and right, that'll be our conversion. Our radius here is going to be between what two things? And our theta is going to be between what two things? 0, 1, 0, 2 pi. There's something that I didn't point out in the very beginning of this that I think I need to point out, but maybe I should wait till the end. But let me mention it now. Okay, our original problem here looked like this, kind of. Right? It was like this. And do you remember we said that when we use these formulas, our normal vectors need to point out away from the solid that it encloses? And do you remember when we said that this green surface right here, that was S1. We did that last class. The normals pointed in the positive y direction, so that was outward. Yes? So they point in the positive y direction. What do the normal vectors on this S2 look like? The y components point in the negative direction, don't they? So when I brought up this formula, I put here normals pointing to the right out the y-axis. That's the formula you would use. What happens if your normals are pointing out the y-axis but to the left? What's that? Negate the whole thing. You make the whole thing negative. All right? So because of that, I'd like to go back and make sure we point that out in the very beginning, that right here, at this point right here, we will put a negative in front because our normals point to left out the y-axis. Okay, I'm doing it here, not before, because this is where I converted to the formula. All right? And so I'm going to go here. Now that negative is going to be here, which means it's here, which means we'll just need to carry it the rest of the way, okay? Sorry about that. I forgot about that. Okay, now let's do our polar conversion now. We're going to convert this double integral. Let's do it. This double integral is now going to become what? Negative double integral. I can put my limits of integration on. They're both constants. They're between constants, so it doesn't matter which order I go here. And then my integrand needs to be converted too. What is x squared? R squared cosine squared theta, or cosine theta squared, plus 3 times what? R squared sine squared theta, right? Times r dr, no, d theta dr. Don't forget that r that comes out of the polar, right, conversion. And then you could distribute that all through. I'll have Wolfram do that for us. Whoa. So let's have Wolfram do this integral, if it feels like it. The heck? So we are integrating. Let's integrate. What is it? R cubed, right, times cosine of, let's say, t, but then we want all that squared, right? Just the cosine part squared. Oh, I said cubed. I didn't put cubed, did I? And then it's plus 3r cubed, right? Times, it'll be sine t squared. Then, how do I say the rest? What are we going to integrate with respect to first? Okay. How do I tell Wolfram alpha that? Put dt, try dt, and then put from where to where? 0 to 2 pi. Let's see how smart it is. I might need some parentheses in here, depending on whether or not Wolfram alpha wants to play nice or not. What the hell is going on with the internet here? I don't have time for this today. Come on. It's thinking. It's taking too long, man. You're taking way too long. Pardon? Oh, yeah, no, I know we could do it by hand. I just don't want to do it by hand. I can do it much faster with this. In fact, I'm just going to close that window out. Close it. You're not reliable anymore. This is much faster. All right, 0 to 1, right? 0 to 2 pi. It's much faster if I type it correctly. Then we have r cubed times sine t squared. I should have had this one ready to go before I came in. Plus r cubed times cosine t, damn it, squared. 3, thank you. 3. For what? Yeah, I typed them backwards. I'll put it right here. And we're going dt first, then dr. Pi. But hold on, we had a negative out front, didn't we? Okay, negative pi. Without going through all that work, right? Okay, so now let's do our conclusion for this problem. Therefore, the flux over the vector field through this surface, the entire surface now, right? We're not just looking anymore at S1 and S2, we want them both. What did we get for the front surface? We did that last class, so we'll have to look. What did we get for it? We got pi. And now we just got for the other surface negative pi. So you add them together, and you get 0. the flux is 0. Understand? All right, let's proceed. Okay, find the flux, the vector field across the surface S, where S is the boundary of the solid half of the cylinder. What I'd like to do here is I'd like to show you the work for this and not go through the work, all right? Because I want to be able to get to 13.9, and we can do this in 13.9, and it'll be trivial in 13.9, all right? So let's take a look at the work I have for this problem. I'll look at my summer. All right. So the idea here is just to be able to follow this, all right? So we have 4 surfaces. No, 3 surfaces. The curve, no, 4. Back, front, bottom, and then this curved top, right? 4 surfaces. This front one we'll call S1, the back one S2, the bottom is S3, and this curved part is S4, all right? Now, let me write down the equations of this thing real quick so we have them on the board. This thing, this backside is touching the YZ plane. Okay, that's on that backside is on the YZ plane. See it? Which means if you look at this as a plane, what is its equation? I mean, not the whole surface, just if that plane right there, x is 0, right? X is 0. That's the YZ plane. And then what about this front side? This front side, the plane equation here is what? X is 2, right? That gives you the whole plane. You can kind of see it here too, right? And then the bottom, what's the bottom? What's the equation of the bottom of this thing? The plane equation. Z is 0, right? Keep that in mind because I'm going to use that. So let's look at S1 first. Since S1 is a flat surface, I know all the normals are always the same, aren't they? All the normals have this direction, straight out the x-axis, 1, 0, 0. And so when I go to choose for S1 which of the formulas I'm going to use, I'm going to be leaning towards the normal one, but hoping that I'll be able to handle what happens when I dot that normal with the vector field. Okay, so I go ahead, I take my vector field, which in the problem was what? X squared, y squared, z squared? I take that vector, I'm going to dot that with the normal. So here it is, right? This will now be with respect to the surface S1 ds. Everyone okay with that? That's the second version of that over there, the second part of that equation on the board over there. Now, you dot these. When you dot them, all you get is the x squared, correct? However, x when you were on S1, y'all just told me when you're on S1, which is this front side, the equation of that plane is x equals 2. So this x squared can become a 4, right? Because x has to be 2 on that S1. Yes? And so now what this is saying is you could take the 4 out, and the double integral over S1 with respect to S really means what? So take the 4 out. The surface area of what? Surface area of what? Of S1. That's what it means, right? I'm taking the double integral over S1 of 1 ds, and the 4 came out. So this integral right here means the surface area of S1. Do you know the surface area of S1? It's half a circle, right? It is a circle, isn't it? What would happen if you square both sides here? The cylinder, because the cylinder, right, is what makes that circle or that shape. If I square both sides there, I would get what? Well, if I wrote this as an equation, that's the edge, isn't it? So if I square both sides, I get z squared equals 1 minus y squared. Is that a circle? Yes, move the variables to one side. That's x squared plus y squared. Z squared plus y squared is 1. That's a circle. So I do know that this is a circle. And so I just need to know the area of half of it. Pi r squared times 1/2. So the radius of this is 1. So pi, and then divide by 2. But then what? Multiply by 4. So 4 times pi over 2, 2 pi. Got it? Make sense? All right, that's S1. I would imagine S2 is going to work almost similar, in a similar manner. In fact, S2 is going to be a little easier. But check out what I have written here for S2. I am going to do the normals again, right? I've highlighted this in red. Why? That's right. When we're doing flux, we want our normals to point away from, right? Away from the surface. You want them to point outward from the solid that they enclose. So the vector coming out this way is negative 1, 0, 0. And so I dot that here with my vector field. And that gives me negative x squared. And then why do I put 0? Because on S2, right, that back side, we said the plane equation there was x is 0. So if you live on that surface, x is 0 the whole time. So you get 0, and it doesn't matter what happens now. It's 0. Is that okay for those two? Okay. S3 would be the bottom. That's probably where I went next. For S3, the normal vectors point downward, right? And so I'm going to use that same formula. I'm going to dot the vector field with the normal vector. When I dot this, I get negative z squared. And again, because the plane equation right there was 0, z is 0, it just becomes 0. Right? Nice. And now for the hardest part of the whole thing, which is this surface S4. Notice there the normals point up in the positive z direction, right? Anytime you're on that surface. And I can look at that surface as being a function of two variables, can't I? It's actually z is equal to 1 minus y squared square root. Now, even though x doesn't appear here, you could still say it's a function of x, right? And so I'm going to use the special case. And because the normals point upward, I do not have to come in with the negative, right? If they pointed down, I would have to put a negative out here. So in the special case, I just go to the formula that I gave you, right? Do your formula, and what it'll come out to be is this, right here, with respect to, this time, area. That's what the special formula gives us. Are y'all following me or not? Camera? Sure? Do y'all want to see this formula, or you trust you could look at it and crickets? We're saying that z was a function of x and y, right? Z was a function of x and y. So I'm using this one. Negative p partial g with respect to x minus q partial g with respect to y plus r. That's what this is. Negative p partial of g with respect to x was 0. Minus q partial of g with respect to y was this. It was some chain rule on that derivative. And then plus r, so z squared. Does that help a little bit? What's z squared? Well, remember, we can't have z in here. Z can't be in this double integral because our variables here are x and y. So I replace z squared with, well, come over to that equation, square z, you get 1 minus y squared. So that's where that comes from. And now you do all this, and this you could do. How would you do this? These would be easy, right? These two integrating these. This, there are different things you could do there. Basic U substitution might work, kind of a clever one, or you could also do trig sub. What about our restrictions on x and y? The region of integration here is a rectangle, right? The ground. So that's why we can say from 0 to -1 to 1. So if you were to do all this, you'd get 8/3, which I won't show. I think we're going to conclude from that. We had the 2 pi here, right, from the S1. S2 gave us 0, right? S1 gave us 2 pi. S2 gave us 0. S3 gave us 0. And S4 just gave us 8/3. So you get your total flux over the entire surface is 2 pi plus 8/3. Got it? Yep. Outward. There's more outward flow than inward flow. We good? If you believe that, we're done with this section then. If you want, you can go back. If you need a better explanation of that, you can bring up the YouTube video. Go take a look at my summer class. That was the day 14, because it was summer class. That was like almost the end. That was day 14 of that summer class, where I went through that and worked through the whole thing and talked through the whole thing. And so if you need to go back and see it, you can. 13.8, Stokes' theorem. So we're going to step back to line integrals right now. All right, we'll step away from the surface for a minute. Well, just for a second. Line integrals over vector fields. So does this formula look familiar to you? I mean, we did this once. This was work. This is how we computed work. It was a line integral over a curve. You had a vector field. We're dotting it with dr. This turned out to be the vector field evaluated on the curve times the derivative of our curve, dt. And there's another notation for this that I gave you back in this section. This one right here. F dotted with capital T, where capital T was unit tangent vector. Unit tangent vector with respect to arc length. Okay? So if you need to go back and take a look at that, that was the way we defined work. So now we're going to look at Stokes' theorem. Let S be a piecewise oriented smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation. What the hell? Let F be the vector field with continuous partial derivatives on an open region of R containing the surface S. Then this is true. So what is it saying? I think I have a picture to help. Let me draw a picture to help. Here's what Stokes' theorem is saying. Let S be an oriented piecewise smooth surface. So let S be a surface, right? That is bounded by a simple closed piecewise smooth curve. So let's say I have a surface, and let's just stick two-dimensional, flat sheet of paper. Everyone agree that that creates a surface? Yes? Got a surface there. It's bounded by this piecewise smooth curve. Then let F be a vector field. So we got a vector field in this space. Also, it says C has a positive orientation to it. Remember what positive orientation meant? Counterclockwise. So C is the curve here, right? C is the curve. S is the surface inside. Yes? What Stokes' theorem says is that if you would like to compute the work, okay, along the curve through the vector field, that instead of doing a line integral, all you need to be able to do is take a surface integral, right? You have a surface that it encloses. You need to do a surface integral with respect to ds, right, of not the vector field, but the curl of the vector field. That's what Stokes' theorem gives us. So it's a way to convert a line integral into a surface integral. And instead of integrating f, we integrate the curl of f. Now, we aren't going to prove this theorem, okay, but it's very useful, very powerful. Reminding you what curl of a vector field is. Remember how we did curl? We did del cross f, and that meant this, and there was a formula for it. So let's see how this would work, all right? How could we do this? How could we use this? Find the line integral over C of f dot dr, where C is the triangle with these vertices, and the vector field is given here. All right, let's see how this is going to work out. Let me draw my triangle here. 1, 0, 0, 0, 1, 0, 0, 0, 1. I have a triangle, right, with those vertices. My vector field in this problem, x plus y squared, y plus z squared, z plus x squared. So if I was going to try and do the line integral over C of f dot dr, can anyone tell me what I would have to do? Where C is this curve. C is the curve. It's the triangle, isn't it? How would I do that? How do I compute that? Exactly right. You would have to come up with parametric equations for the 3 different line segments, wouldn't you? Then you'd have to do your work integral on each one of those. Yes? But Stokes' theorem says that if you have a line integral, and that line integral encloses a surface, in other words, if you have a triangle in there, right? Now that triangle is in 3-dimensional space, yes? If I can figure out what the surface integral is of that triangle, then I can do this line integral, right? Converting the line integral to a surface integral. So what we would need to do is to come up with a way of representing that surface. Can anybody think of a way we can represent that surface? What does it look like to you? It's a plane, right? It's a plane. So how could we find the equation of that plane? We could cross 2 vectors on the plane, right? That would give us our normal. And if we did that, I'm not going to show the work, we would get that the normal vector on that plane is 1, 1, 1. So that would give us x plus y plus z, and then this would equal 1. So just, if you went through the work, and I'm not going to, you would take 2 vectors on there, cross them, get your normal, plug it into the equation, and this is what you would have. Can you all trust that you would get that? Okay. Now, because that is a surface, right, It is a surface. I can solve that for either x or y or z. I'm going to solve it for z, make it 1 minus x minus y. And can't I then say that z is a function of x and y? Which means I have a special case here, don't I? Don't I have a special case? I'm going to try and turn this into a surface integral, what we just did in the previous section. So what's the formula that we're going to use? I'm going to write a couple of things out here. We have that the line integral over C of f dot dr, which is what the problem asks for, should turn into the surface integral over S of curl F, right? Curl F what? ds, right? Look. This will turn into this, right? Just keep in mind that this curl F is a vector field, isn't it? This is a vector field. The curl of F is a vector. So we get a new, we start with a vector field, we take its curl, we get a new vector field. So this surface integral is really like f dot ds, which is what we were doing all the last sections. It's not this f, it's the curl of that f that we're going to be using. You all okay with that? Okay, so let's get a couple of things here. Let's actually figure out what the curl of f is. How do you find the curl of f? You do del, which is this. You cross it with the vector field f, which was given to us in the problem to be x plus y squared, y plus z squared, z plus x squared. So put that in here. And that looks like something real nice, doesn't it? Ew. Okay, so what's the first component of this vector? Partial with respect to y of this, which is 0, and then minus this and this, so negative 2z. Oh, that wasn't so bad. Okay, now the middle one, so cover up the middle. Partial with respect to x of this would be 2x, but then we change the sign. And then we go the other way, which would be what? 0. So we get negative 2x. And then finally, you get negative 2y. I won't show it, but that's what you get there. So that's my curl. That's my new vector field that I'm going to be doing the surface integral on. So now what we'll have is the double integral over S of negative 2z, negative 2x, negative 2y dot ds. Okay, that's my curl vector. But we said that this surface was a special case, isn't it? It's a special case where our z is a function of two variables. So from last section, when z is a function of x and y, we can turn this into something nice, right? A double integral over d, where this is our p, this is our q, this is our r. Not the original vector field, right? This is our pqr. It's the curl of f that we're looking at. So what's my formula? Hey, is this on your formula sheet that didn't I give y'all a handout? Can you get that out real quick if you have it? I want to make sure that there was not a typo on the formulas on that. If I even gave you the formulas on that. Who has it? Did I give you all special cases on there? Can I see it real quick? I only gave you one of the special cases. Hold on. G of x y z. Yeah, I only gave you the first one. Do y'all see that? I only gave you all the first special case on that formula sheet, which is this one right here, right? That's the only one that's on that formula sheet. So the others, you should probably have handy on your final. You can have a sheet, or you can have that sheet that I gave you. You can have your own cheat sheet. Just can't have worked out problems on it. As long as you can have a reference sheet, that's okay. So I'm going to use this formula. Are y'all following me or not? Double integral over d. We're going to convert it to d. We'll have negative p partial with respect to x. Let's do all that. So this will become double integral over d. And then what's that first piece going to be? Negative p. So for us, 2z. Partial of g with respect to x. What's partial of g with respect to x? Negative 1. And then plus, because it's minus q, so plus 2x. And then what is partial of g with respect to y? Negative 1 again. And then the last part is r by itself. So r by itself for us is just negative 2y dA. We good or not? I feel like y'all are already like shutting down for the semester. Next week, you shut down after next week. Yay? Yay? Yes? No? Yes? What variables am I allowed to have in here? X and Y, that's it, right? Z can't be here. So I need to replace Z with, what was Z? Well, Z was 1 minus X minus Y. So we do that. We plug in, and we get, I'm going to pull negative 2 out of everything. You should get this. Actually, this whole thing turns into a 1 dA. Because what happens is when you replace Z with 1 minus X minus Y, it's going to wind up canceling things, and you're going to be left with a 1, or negative 2, and then you just pull the negative 2 out, so you should just get a 1 there. What does this mean? What does this double integral mean? What's the area of D? What's D for us here? It's the domain, right? The domain of this right here, which is the ground, isn't it? It's the ground down there. It's the X and the Y, isn't it? What's the area of that triangle? 1/2 base times height. So 1/2. And then you multiply that by negative 2 out front. So you get negative 1. Because this area right here, area of D, equals 1/2. Now that, believe it or not, was probably easier to do than it would have been to do by line integrals. How about this problem right here? That was a take-home test, right? Where you did this line integral around this thing? Yes? How many of you actually did the parametric representation of the line integrals and went all the way around? How many of you used this theorem? The theorem was what? You can convert a line integral around it to a double integral over the regions that it encloses. Green's theorem. That's right. So Green's theorem turns out to come out to answers pretty quick. But could you do it with the line integrals? Yes. Same thing with this. That's what I'm trying to get at is with this, we could have done the line integral. Okay, we could have. What the heck? I've lost where I am. I've lost where exactly I just was. This is earlier, right? I have no idea where the notes I just were writing are, what folder they're in or anything. I might have been in the summer one. Well, it's going to be hard for me to find it. Let me see. Yeah, that's it. All right, I'll have to move all that over later. But so what I was getting at is you could have done this with just the curve integral. You could have gone around this curve, parametric representations, and done all that. But you could also do this way. And this isn't too bad. This integration's not too bad. I would be willing to bet that it would be faster this way with Stokes' theorem. Questions? Let's see what else we've got here. Find the line integral f dot dr where c is the circle, x squared plus y squared is 16 with z equals 5. And here's our vector field. So what are you thinking? We have a circle C, x squared plus y squared equals 16, but z is 5. What does this look like? Kind of a cylinder, but it's z is equal to 5, right? Not z is between 0 and, it's like a floating circle, right? It's got this circle, this ring like this. Yes? And it's 5 units high, so the center of that thing is up here at 5. If we look down on the ground, the radius of this thing is what? 4, right? 4 this way, and then 4 this way. So we come up to that point and that point. I hope that makes sense. So your floating ring up there, right? Yes? I want to do this integration over that curve of this vector field. So you might be thinking, well, what's the big deal? I just find parametric representation of the circle. That's not hard to do, right? Can you draw that circle for me? With the vector curve of one variable, right? Because it's a curve, not r of uv. 4 cosine t, 4 sine t. What about your z coordinate? 5, right? T is between 0 and 2 pi. That draws it, right? Draws you circle, up 5 units, fine. So to find the line integral, you'll have to be able to take derivative of this. Not a big deal, right? The problem is that you have to plug the parametric representation of this into the vector field. That's the problem, because look, do you want to actually do this yz, y times z, not so bad, but then 2 times xz, that's not so bad, but look at the next one. E to the xy, e to the 4 cosine t sine t, 4 sine t. That's not something you're going to want to be integrating, right? So maybe Stokes' theorem will allow us to make this much easier. In fact, it does, right? Think about it. Look at this way. This circle encloses a surface, doesn't it? That surface, I can call it S. And so as long as I can compute the curl of F, I should be able to convert this thing over. So let me find the curl of F. Curl of F will be del yz 2xz e to the xy. Let's go ahead and do that. Or would you like me to just write down what it is? Write down what it is? Well, check this out. I'm going to do you one even better. Check this out. That's what I'm trying to do, right? I know that that's going to become a double integral over the surface S of the curl of F dot ds. But I noticed something very nice about my surface. The normals on that surface are always the same, aren't they? Aren't they? So this formula, I could use this one. Instead of dot ds, what can I put here? Dot n ds, right, without the vector? These are the same thing, aren't they? That's what we were doing last section and earlier today. This means this or the third version, which is this one. We haven't used a whole lot of this, have we? This last one. But this is good if I know what that normal vector is. I do know what it is. And why am I doing this? Why am I kind of avoiding this curl for a moment? What is the normal vector on this surface? 0, 0, 1. Which means when I dot it, right? When I dot it with the curl, what's the only thing that's going to be left? The z component of the curl. Do y'all see that? Everything else is going to zero out, so I don't care what it is. So instead of going through and finding all this freaking curl stuff, let me just find the z component of it. So what would it be? Cover this up. Partial with respect to x of this, which is 2z. Partial with respect to y of this, which is z. So I'm doing 2z, taking away z, which is just z, right? So I'm going double integral over S of, I have no friggin' idea, I have no idea, z dotted with 0, 0, 1 ds. And that's just going to turn into double integral S of what? Z ds Can I make that any nicer? There you go. Z is 5. Look where you are, right? I mean, if you're on this surface, Z is 5. 5 ds, which is 5 double integral of over S of 1 ds And what is that? That's the surface area of, the circle, right, of S. Do you know the surface area of S? Pi r squared. What's its radius? 4. So 16 pi? Yes? So this is going to be 5 times 16 pi, which is 80 pi. So the line integral that we were trying to look at is just 80 pi. That would have been relatively impossible to do had you tried to do it with the normal line integral. But it becomes a very simple problem here, converting using Stokes' theorem. I know, I hear you. Let's see, is there anything else? Is there more? Find the line integral f dot dr, where c is the curve of intersection of the plane x plus z equals 5, and the cylinder x squared plus y squared equals 9. So x squared plus y squared equals 9 is a cylinder. You're coming through with the plane and you're cutting it, right? Where you cut it, it creates a curve. And we'd like to know the line integral along that curve through this vector field. So what are you starting to think now? When's next Monday going to be over? Is that what you're thinking? I have a cylinder. I'm cutting it with a plane, which is going to give me something like this. Right? That's my curve C. It's like an ellipse, right? So it's not like the last problem because there's a tilt to this, isn't there? This has an equation. What did I tell you the equation was? X plus z equals 5. Right? So do you agree we could do Stokes' theorem here? We could? We just have to come up with a way of representing this surface. You think you can represent that surface? Yeah? I hope so. Do you know I'm looking for you for guidance here. I mean, I'm trying to see if y'all are catching on to this. The reason why is, I mean, this is very similar to a problem that you see on the final. So I want to make sure like you have some concept of what you need to do here. You're asked to find this. And your vector field is x squared z, xy squared, x squared z, xy squared, z squared. That's your vector field. So as looking at this as like a polar conversion, is that what you're saying? Or you're saying, no, doing like a, trying to represent the surface parametrically, like with R of UV, you could do that also. But before we do that, can we just like figure out if we're going to use Stokes' theorem, what the curl is? Like see if the curl turns out to be ugly or nice? What's the curl of F? This is what I'm going for, right? Curl F ds. That's what I'm shooting for. I'm trying to turn this into this. Okay? Curl F for us Is it good or not? So start off with the first part there. Partial with respect to y of this is 0. Partial with respect to z of this is 0. So we have 0 for the first component. Okay, middle one, partial with respect to x of this is 0. Partial with respect to z of this is x squared, but then it's negative, but then it's negative. So it's just x squared? Yes? Then the last component, partial with respect to x of this is y squared, and then with respect to y is nothing, so just y squared here. It's not too bad looking curl, right? Not a bad looking curl. Now we have two options. Are we going to look at the normal vector of this thing? Here's where we have to be careful. If you're going to do the normal vector, then what we've been relying on is then knowing the surface area of whatever was left. And that's a tilted circle, so it's not, the surface area is not going to be clean, is it? This one over here says I don't need to know the surface area of that tilted thing. I just need to have restrictions on my parametric formula, which you were saying we could draw this parametrically. How could you draw that thing parametrically? Good question. It was 3, I think. X squared plus y squared is 9. Let me draw that on our picture. X squared plus y squared is 9. Okay, so now can we go draw the, let's come up with the R of UV, because I'm going to use the cross product on this one. R of UV. So you're saying what? 3 cos, well, I'm going to use U and V, but keep in mind here, we're trying to draw this surface, right? I was trying to rotate. I can't rotate. I just drew the freaking thing. If I rotate that, right, and look at it from the top, it looks like a circle, right? The only thing that's changing is the z component. So draw me a disk in the xy plane. That's going to be what? U cosine V, U sine V? Do you agree? Where U is between where and where? 0 and 3, and then V is between 0 and 2 pi. Now what about that last piece? What's my Z? It's the plane equation, so it's just what? Solve this for Z, 5 minus X. But X for us is what? U cosine V. Now I could do this, right? I could do this, and I could go through and I could find the cross product of the partial derivatives, right? And then go into my formula. But nobody has pointed out something else I could do. I said the normal part, right? I said looking at the normal, not really a fan of that because then I'm going to need to know something about the surface area there. But is this a special case? Is your surface a special case? Yes, it's Z is a function of what? X and Y, isn't it? I could use that also. Which one do you think is going to get you there the quickest way? I mean, I'm looking at this partial going, I don't know if I want to do partials and crossing. Do you? I mean, you could, right? You could go down this road. There's nothing wrong with that. But the special case seems to be more straightforward. So what do y'all want me to do? We only have 20 minutes left. I think this is our last example in this section. Yeah. Special case. Me too. I like that idea. So, special case. I know that my Z is equal to 5 minus X, right? So Z is a function of X and Y. And I know because of that, that a double integral, it's going to be the double integral over D, right, of, bringing in that formula, negative P, right? What's negative P for us? Remember, this is our PQR here, not the original vector field, right? This is our PQR. It's the curl that we're looking at. So PQR. So 0, that won't matter. And then it's minus q, which is going to be for us minus x squared, times the partial of g with respect to x. What's the partial of g with respect to x? G with respect to y. Pardon. This first one had the partial of g with respect to x. The second one has partial of g with respect to y, which is 0, right? And then the last part is just plus q. Or plus r, sorry, which would be for us plus what? Y squared. dA. And so this is double integral over d of y squared dA. Can I have y in here? What were the variables that I had? X and y. So that's okay. I can't pull y squared out, though, right? And make this, oh, it's just the area of d. No, you can't do that because it depends on that. So now you're back in double integral. You're trying to do the double integral of y squared. And this is your picture. Your x and y are the ground domain. I need you to define the ground domain of this surface for me. Circle. So, polar. You need to go to polar now. So this is now going to go to polar, which means I'm going to say that x is equal to r cosine theta, y is equal to r sine theta. My radius will be between 0 and 3. My theta will be between 0 and 2 pi. And how can I rewrite this double integral then? Zero to 3, 0 to 2 pi, right? What's y squared? R squared sine squared theta, but then times r, so r cubed sine squared theta d theta d r, which you could do the rest. Okay? At that point, you're there. Questions? Yes. This right here? Okay. So in this special case, that's in 13.7. Which equation for what? Yes, it was the plane equation. It's what draws our surface, right? What draws that surface is that plane. The fact that I'm restricting it to a circle is what makes it look like an ellipse up there. So it's just the surface equation. Yeah. This is my vector field, which was the curl vector. You good? Okay. Any other questions? All right. The last thing that we'll talk about this semester is 13.9, the divergence theorem. I don't have notes to hand out for this because there's really nothing to talk about. There's not a whole lot to write. This is also known as Gauss's theorem. You might hear people refer to this as Gauss's theorem. Gauss is a mathematician. If you haven't read up on him, you should. Okay, so check this out. This is what the divergence theorem says. It says, let's say you have a solid. Let's do something very simple, something that looks like kind of like a brick. Some three-dimensional solid. And we'll call this solid E, is the solid. Then that solid is enclosed by surfaces, right? There are surfaces that enclose the solid. In this case, it looks like there would be what? One on top, one on bottom, one left, one right, one front, one back. Maybe 6 surfaces make this thing up, right? Gauss's theorem gives us a connection between the surface integrals and the integral on the solid inside. And it's this. The surface integral f ds. So if I have a surface that encloses a solid, even if that surface is made up of multiple surfaces, then if I want to compute that flux, right, that's flux, that all I need to do is do the triple integral over E, the solid that it encloses, of the divergence of F dV. This is absolutely fabulous, this theorem, because it's going to trivialize a lot of flux problems. Okay, let me give you an example. Let's look back at the problem we did earlier in 13.7. It's the last problem we did. Remember this one? Drew it on the board. What did we come up with on this? Was it like 2 pi plus 8/3? No? That was... Did we get, look back, someone's been writing stuff down today. Was it 2 pi plus 8/3? Or was that the previous problem? Dun, dun, dun. Okay, I'll go back. 2 pi plus 8/3. There we go. All right? We got that earlier, right? And I have the vector field up here, right? Here we go. We've got this. So check out how freaking nice this is going to be. I'm trying to find the flux over this entire thing. We had to break it into 1, 2, 3, 4 surfaces. We had to look at each surface. It wasn't too bad, but it took us a little while to do it. According to this theorem, if the surface encloses a solid E, which it does here, then all I need to do is a triple integral over this solid, over the region E, of the div of F. So what's the div of F? F being this vector field, it's del dotted with the vector field. All that means is you take the partial here, plus the partial here, plus the partial here. It's partial with respect to x, y, then z, add them all up. So what do you get? 2x plus 2y plus 2z. That's pretty easy, right, to get a div? And I just need to do a triple integral of that over the solid. Look, there's no vectors in here. Do you see that? I mean, we have a vector field, right? We started with a vector field. And this whole vector field thing, dot ds, all just becomes a triple integral with respect to volume. This is an integral we did in the very beginning when we started doing like double and triple, before we brought vector stuff into anything. So I just need a way of you please defining the solid E for me. How can you define this solid E? Well, you need to be able to give me a restriction on x, y, and z. So can you give me a restriction on x? By the way, this x went from, do you remember, 0 to what? 2. So I can tell you right now my x goes from 0 to 2. And then my y goes between where and where? -1 and 1. And then my z is between what? The ground and the top. But the top was this, right? So 0 to square root of 1 minus y squared. That's it. I have my limits of integration right there. It's just a triple integral. That's all it is. So I'm going to rewrite everything now. Which would be 0 to 2, negative 1 to 1, 0 to square root of 1 minus y squared. And what am I integrating? 2x plus 2y plus 2z, but I'm going to pull the 2 out of everything. Just make it x plus y plus z. Maybe I should have left it in there. D what? Z d y d x. And then you integrate. I'm not going to go through it, but you would integrate that. That one's a little bit tough. I mean, like the integration's a little rough on this one. But you could still get it. All right? Let me give you another example. I'm just going to put dot, dot, dot here. All right? Let me give you a different example. Do you remember this problem? Find the flux of the vector field yzx across the unit sphere. Let me show you what we did for this. The flux across, I'm in the wrong day here. This would have been probably here. Trying to find where we did the flux across the unit sphere. Do you all remember this problem? Yes? It was a little bit of work, okay? We had to come up with the parametric representation. You know, we had to find what RU cross RV was. We used our spherical coordinates. If you look in your notes, it was a bit of a job to get this to come out. And when we were done, our answer was 0. All right? It was 0. Now I want you to see just how easy this problem is with the divergence theorem. So, what's my vector field? I'm going to do this up on the board. I'm not even going to write it down. My vector field is here, right? The unit sphere looks like this. It encloses a solid, doesn't it? The solid it encloses E is in there. I'm going to have to be able to define E for this triple integral. But what's the div of F? Partial of the first component with respect to x, which is 0 plus 0 plus 0. So it's the triple integral over E of 0 dv, which is 0. There's no work at all. See what I'm saying? I mean, that is as easy as it could possibly get. But without that divergence theorem, that problem required quite a bit of work for us to show it was 0. It's a very valuable thing. So as you know, if you start to get other problems, you know, in physics problems and stuff, and you're trying to find fluxes through cubes, things like that, you always want to take a look at what the vector field is and look at its div. You know, if the div is nice, then it's the way to go, right? Okay, we're done. So I've posted the past couple of exams that I've had, and I don't want you to get like too focused on just that, you know. I would like for you to consider the possibility that there will be other things from the homework. Probably would be best to bring it up this way. So just to give you an idea of what I asked. You want me to talk about this or not? I mean, we can cut it loose if you want. So some things I asked. This was a change the order of integration problem. Triple integral over a solid. Let me see. Another triple integral. This doesn't look like it has the problems. I need to send you the problems. This doesn't have the problems. It's just the answers. Line integral. Oh, line integral over a curve that's not closed. So you have to do the parametric representations of the curve. Find a potential function. So that partial integration, remember that? This one is Green's theorem. Vector field, closed curve. Instead of going around the curve, just look at the region inside. So that's a Green's theorem problem. Hard to say what this is. Oh, find the equation of the tangent plane to a surface. So to find the equation of the tangent plane, you cross the partial derivatives. That'll be your normal vector. Then, see, find the surface area. That looks like what that is. This one looks like a flux or something because you have S1, S2, S3. This is definitely a flux problem. This one's interesting. You have this shape here. So, what's that? There you go, Stokes' theorem. Divergence theorem. What was that? That just gives you some sort of idea of how many problems were on one of my finals. About 14 problems, varying all the way back from double integration when we were doing, here's a region, change the order of integration over all the way up to divergence. But you can kind of see how it's laid out. I mean, I can ask you one flux problem and it covers a lot, like polar. It's all covered in there, right? I mean, it's not like I have to test you, like show me how you do a polar integral. It's kind of built in now. Okay, we're out of time. Any questions for me? Yes? No, it won't be. Because, again, those are a little too time-consuming. Yeah, I mean, no, I don't plan on putting it on there. Unless you're requesting. Are you requesting? No. Our test, to be clear, is on Monday. Unfortunately, we're a Monday test. So 11 to 1:45 in this room. And then for something for homework? No? On the day of the final, right? Okay. So I'll be looking, make sure you bring your homework on the day of the final if you have been keeping up with it. And I'll send out a couple of problems in email for Div and Stokes's and stuff if you want to go look at those. Okay. Hope you learned something. Regardless of what happens with the grades, hope you learned something. See ya Monday. Yeah. I'll be around if y'all need me. I do should be equivalent to the work the gravity did